All right, perfect. Yes, so with that, let's switch to today's agenda. So you can find the home of this meetup, obviously, on meetup.com, where you probably found today's session too. And we do have exciting speakers today. We're gonna start, and I'm gonna zoom in here too a little bit more. We're gonna start with a session from our friends over at Modin, who are gonna present on how to speed up your Pandas workflows by just changing a single line of code. So we're gonna see how that works. And yeah, welcome Alejandro Herrera here and Devin Peterson from Modin. From Ponder, who will present on the Modin session. And I also excited to welcome a speaker, Justin Chiu from Amazon Alexa AI, who will present second today on optimizing large-scale distributed training jobs using Nvidia GPUs, DeepSpeed ZeRO. So we're going to learn what's behind there, and Kubernetes on AWS. So a great lineup for today. I'm super excited to have our speakers. And with that, I would say no further ado, and I'll hand it over to Alejandro.
Thank you, Antje. Thanks for having us. Devin, do you want to introduce yourself while I share my screen?
Yeah, sure. Hi, everyone. My name is Devin Peterson. I'm the CTO and co-founder of Ponder. And what we're going to be talking about today is some of the work that I did actually as a PhD student at UC Berkeley, and kind of the open source project that kind of emerged that basically became my PhD. Fortunately, I graduated last year, so I don't have to write as many papers, but it is nice to be able to continue to work on, the work that started as, my PhD project. And Alejandro, do you want to go ahead and introduce yourself?
Sure. Thanks for having us, everybody. I was so excited by the Modin project and what Devin and the team were building, that joined at the beginning of the year to become an architect and support the open source project, as well as the company that we're building around it across a range of different functions. So excited to share a little bit about the project and what we've been doing with the project with you all today. Devin, do you want to jump into it?
Yeah, so a lot of the reason why we started this project kind of boils down to a scalability problem that we recognized in data science. And so when we say scalability problem, a lot of people's minds immediately go to compute, but that's not actually what we're talking about. It's really easy to actually spin up more compute. It's easy to get access to more machines. We have systems now that can scale very large. Actually scaling to larger data, that's not really the biggest problem, the biggest bottleneck anymore. What we see is actually that data teams have a scalability problem. It's more difficult to hire. It's very difficult to scale your data teams. And even when you do scale your data teams, what happens is more data scientists doesn't always equate to having more insights or more production jobs or more production models. We see that there are a lot of challenges, not only in scaling the data teams, but also in making those data teams productive inside of data science, or like the broader data science organization. And so really what we're talking about is that the kind of data tooling landscape and the fragmentation of data tools in the data stack really limits the productivity. And so at Ponder, we kind of have this this core value, or this core tenet, that that tools should be working for the data scientists. Data scientists and data teams shouldn't have to work around the tool landscape. They should just be able to kind of be productive and be able to work in the tools that they're kind of comfortable with and familiar with. And so, obviously Pandas is one of the most popular languages, the most popular tools. I say language, some people might not think of it that way, but I think it's becoming more and more of a language, especially as tools like Modin kind of gain more mainstream and popularity. But Pandas is flexible. It's easy to prototype things quickly. It's widely adopted, and it's very, very flexible in what you can do. That you see here, there are all kinds of different operations you can do that range from, joins and relational database style queries. There's also linear algebra style queries that you can do. There's also some spreadsheet like stuff you can do with like pivots and that sort of thing. So there's a lot of really powerful tooling that Pandas kind of unlocks for you, but it doesn't really scale. And so that's where we get to kind of the big problem that we're trying to solve. We put Pandas as easy to use here. It's flexible, it's expressive, it lets you be agile with your work. Some people might not argue that it's easy to use because they always have to Google things, but the answers to your questions are typically a Google answer away, and you don't have to spend hours trying to debug, partitioning problems or your cluster or that sort of thing. So it is quite a bit easier to use than big data frameworks. And when we look at big data frameworks, they have the performance, they have the scalability, they have the robustness. And what we're trying to do is basically give you easy to use, but also scalable systems. And Modin is basically what powers that. And Modin is what we're supporting at Ponder. And so with Modin, it was designed from the ground up to be a drop-in replacement for Pandas and to allow you to scale. And so as a drop-in replacement, the kind of hook here was scale Pandas with a single line of code. Here's the line of code. Basically, you change your import statement and it should drop in. And so what that means is that basically, read CSV, you get better performance, better scalability, something like mean and group by mean, and all of these things are giving you not only better performance, but better scalability as well. And scale is really where a lot of these things start to break down, as we'll discuss in a few minutes. Modin itself has been very widely adopted. More than 3 million installs, more than 100 contributors, used in some of the largest organizations in the US, ranging from financial to automotive to some ed tech companies, basically in every single vertical that you could imagine where Pandas would be used. Modin has been adopted in some companies in those orgs. So we also, I mentioned at the beginning about my PhD and about how, this was my PhD project in effect. There's a lot of actually deep core systems that I'm happy to talk about. And there's like some, cores, computer science theory that we had to basically, kind of start from the ground up. And Modin really is a system that we built starting from first principles. Happy to talk about these things. But as a research system, we were basically able to keep the Pandas API as it is and change everything about how it executes and start having a lot more, deterministic and scalable ways of implementing the algorithms that Pandas kind of lets you use. So yeah, and 7.5K stars. I would encourage you, if you're interested, we do have a Slack. Feel free to join the Slack, modin.org/Slack. I'll put it in the chat here, but yeah, I feel very fortunate that my PhD project was so widely adopted because, I just thought it was an interesting and cool project to work on, and it turned out to solve a lot of people's problems.
Thank you for the context, Devin. Just to double click into more of that motivation behind the project and why we're so focused on building this out. A lot of the times we're speaking with users across small tech companies to big Fortune 50 companies, and we're seeing common patterns in how they build data solutions. A lot of them like to start with Pandas, as Devin was saying. It's flexible, easy to use, and a lot of people learn it in week 2 of their data science boot camps. So they start prototyping, doing their EDA here with Pandas. What we see is, as they try and use more data, they have scalability issues with Pandas because of the way it was designed. And so we see a lot of out of memory issues and long running jobs. And the only, real solution that the teams that we work with tend to have is totally rewriting their code and basically migrating to a different framework that supports whatever it is they're trying to do. So they rewrite it to test it at larger scale. Then when they want to move to production, they have to rewrite it again and refactor. As they deploy it in production, they inevitably have issues. And so we see this feedback loop where the people that initially developed the models aren't really involved in deploying the models into production. And so when something does go wrong in production, you have a ton of several different teams trying to tackle the problem from different angles, and it really slows down the productivity of these teams. So with Modin, what we've been doing is trying to offer data teams a unified interface for analyzing data that they can use throughout the development lifecycle. So that's really what we've been focused on. Let me pause there. I have a quick demo to show you guys, but any questions that we can take while I switch over to the demo?
Yeah, we have two questions here coming in. I maybe just want to quickly call out one comment here. Really love the build from first principles approach. If you wanted to learn more about it, can you recommend some resources?
Yeah, we have lots of things available. It depends on how deeply technical you want. I'll share some links in the chat though. My thesis is the most deeply technical, obviously, and it goes in the absolute deepest detail. But I've also given some higher level talks and those sorts of things that would definitely help. So
Perfect.
I'll share some links in the chat.
Yeah, thanks, Devin. Thanks so much. And then one question, you might touch on that later. I don't know, any benchmark data comparing with bare bones pandas?
Yeah, so we've published a lot of benchmarks in peer-reviewed journals, and we'll also share some demo here that goes over that. But yeah, there's also some stuff on the documentation. I'll also share some links if I can. So
all right, thanks.
We have our emails at the end of the presentation. Feel free
yes.
to ping us directly if you have additional questions, or if the resources we share here don't hit exactly what you're looking for. So this is a notebook just to show you a quick demo of how you can try Modin within a couple of minutes. The version that we're running here, so Modin is infrastructure agnostic and can run on different compute engines. The case we're looking at here is defaulting to Modin on Ray. All you have to do is pip install into whatever environment you're working in, ideally Python 3.8 or later. And to get started, all you have to do is change the import statement, as we see here. The use case we're looking at is the famous New York City taxi data set. We're running 23 gigs on a workstation. Feel free to check out the link if you want more details on the data set. So we imported native pandas as old PD just to show a side-by-side comparison of Modin versus pandas. Somebody was asking just now about, Modin versus vanilla pandas. This is what that looks like just on the first read. We're reading in the CSV, and you'll see that the syntax is identical between Modin and pandas. That's really what we're striving for with our project, is making it a drop-in replacement. And here we see that just on the read line, we're getting pretty significant improvements. I think this is over 5x speedups. As we go to other operations like joins, we also see pretty significant speedups. This is, I think, almost 3-4x. The idea here again is to make it, the culmination of all of Devin and the team's PhD work, make it easily accessible to anybody with a week or two's worth of Python training. That's really the core here. I see a hand. Sherry has a question. I don't know if I see the question.
Yeah, you can keep the questions, post the questions here to the chat window and we'll get to it.
Okay. All right, so I'll just keep going. And Sherry, please drop your question in the chat. So here's another example. I think earlier we saw the read. Here we're seeing a count. And finally, I will mention, while we pride ourselves in our unparalleled coverage of the Pandas API, we still have a little bit of room for additional implementations and optimizations. So there is a small fraction of the Pandas API that we don't support right now. I think it's around 8% now. And so when that's the case, we fall back to Pandas. The team took a pretty systematic approach to identifying which 90% we wanted to support first. So we scraped a bunch of notebooks from the web and used that to prioritize coverage of the Pandas API.
Yeah, we were very scientific about this, actually, like to a fault almost. So the fact that it isn't supported now doesn't mean that we can't support it. Like I said, we started from first principles, which basically means that we developed a core theory first, and then we started building upon that theory, and now we have basically an implementation that we're basically implementing this theory and the kind of the theoretical foundation. So yeah, and we did start with scraping a whole bunch of notebooks and looking at what people are using. If something isn't implemented, though, it will still work. That's the point of it falling back to Pandas, is like it uses Pandas. You'll still get this kind of same issue of single-threaded execution, though, which Alejandro's about to talk about. So
exactly. So how does it work might be a natural next question. We talked about the challenges with Pandas. We saw that Pandas is single-threaded, and because it's single-threaded, when you're running in the cloud or on your local machine, you have all these wasted cores, right? That's what's causing you to run out of memory. That's what's causing these slow-running jobs. And so by design, Modin was implemented to distribute that Pandas work under the hood on whatever hardware you're running on top of. So that's really how we're able to deliver those speed ups and that scalability. As you scale your infrastructure, Modin scales with you. So if you're running on a cluster and not just on a single node, you're able to use Modin in the exact same way. Import modin.pandas as PD. Same thing here. What else, Devin? What do we want to mention here?
Yeah. So this is just a follow-on theory. So we have like, I know we keep talking about the theory, but there's like this core data model and a data frame algebra that we derived, and we basically have put a lot of work into figuring out how to optimally parallelize everything that you can do in Pandas. So a lot of times you have to sacrifice performance if you want flexibility, and we're basically able to kind of get as optimal of performance as we can while still having the same flexibility. Yeah, I see there are a bunch of questions that have kind of popped up, so why don't we take some time to answer these, because I do want this to be interactive. I prefer interactive.
Yes, we do have a couple of questions here. I think we can slightly group them together. So a lot of questions around the infrastructure, how Modin is running. Does Modin need another distributed framework like Ray or Dask, or can it run on its own? Does it work on CPU hardware or GPU as well? Let's maybe start with those two.
Yeah, so we leverage Ray or Dask. We can also leverage things like MPI and Python multiprocessing. The Ray and Dask engines are a bit more mature in terms of executing underneath of Modin. But yeah, we don't run anything kind of natively. Python, as you may know, is well, multi-threading is a big issue, and I think there are some efforts to kind of get rid of that are hopefully on the horizon. But you need some multiprocessing in order to work. Python multiprocessing is typically slower than both Ray and Dask, so we just leverage those existing systems, and they're good. We didn't need to like reinvent the wheel when it comes to multiprocessed systems. But Modin basically does a lot of the it does all of the kind of partitioning, the distributed workflow and everything, and it uses these as like, you know, task schedulers effectively. The question about GPUs is interesting. We do have a prototype. I've prototyped, like I was a PhD student, so I got to prototype basically everything. We do have a prototype that works on GPUs in a distributed way, can leverage Ray or Dask, but it's probably not ready for prime time. If you're interested in that, I'm happy to talk about it. But the architecture itself does support that, which I think was the core question there. So.
Yes, and yeah, a couple of more questions around the architecture here. Let me see. Does Modin run natively on Apple Silicon?
Yeah, it can. Alejandro has an M1, so yes, it does. I don't personally do it, but yeah, we have people running Modin on Apple Silicon.
And just to add on to Devin's question about infrastructure, or Devin's response to the infrastructure question, what we're showing here is that out of the box, Modin runs on Ray, Modin runs on Dask. This is kind of a longer term roadmap slide that we've been building towards. And so on the ponder side of the equation here, we're building a bunch of really neat stuff around using databases as our backend, which is something we're really excited about, being able to push down Pandas into the database versus having to pull everything into memory every time you want to do anything. So that's, I guess, the other half of this picture.
All right. And we do have a question, I think that comes up often. How does it relate to Kubernetes? And then maybe as a follow-up then, which is a bigger one, around the Spark ecosystem, right? So does Modin support Spark as a backend computation engine? Is that because Spark adopted to build Koala? So a lot of questions around there, and then around the data frame and Spark data frame, maybe also in terms of performance.
Yeah. So how does it? So I'll start with the Kubernetes question. Modin. So we have customers and users who are using Modin in Kubernetes clusters. So Kubernetes is kind of the infrastructure layer that Modin can sit on top of, and so it's similar in some respects, but I would say that that's kind of the relationship between Modin and Kubernetes. The question about Spark as a backend computation engine. So Modin can be run within Spark clusters, and happy to kind of go into the rabbit hole that is how that works. But you can spin up a Ray cluster within a Spark cluster. You can have some. There's a project called Spark on Ray, which kind of emerged from Intel, I believe. And so you can use Modin on top of Spark clusters. Now there's a question about koalas and you know, the nature of Spark's API. So Spark itself as like a MapReduce engine, it scales very well. They have a data frame, and there's some questions about this, and I know it kind of gets into like the nitty-gritty weeds of data frames and data frame implementations and the differences there, but this is my PhD focus, so I nerd out about this from time to time. I apologize in advance if I go too deep. Koalas itself has to deviate from Pandas pretty significantly. So Modin's targeting being a drop-in replacement, right? And so it was targeted towards that since the beginning, and we kind of built with that in mind. Koalas is trying to basically like almost staple this Pandas API on top of the existing Spark data frame implementation, and so they had to make certain design decisions that caused certain challenges. Alejandro, would you go back one slide? There was a question about performance with Spark. So Spark Spark has a lot of overheads related to the JVM. Sorry, the other way. Back.
Oh, the benchmark.
Yes, this.
Yeah. Got it. Yeah.
So Koala's here is this is our VLDB paper from I think it's published this year or last year. VLDB is one of those that has a rolling deadline. So but it's published in VLDB, and the green line here is Koala's, and a lot of times Koala's isn't even faster than Pandas itself. And so the fact is that it's not necessarily trying to be right. It's trying to scale. And so the aims of the projects are kind of different. And so in order to be, completely fair, I think that, Koalas does what it tries to do, in that it's trying to make it easier to use Python, like to have an easier Python API, but it doesn't feel very Pandas-like. It still feels very Spark-like, and you still get errors that look like Java stack traces. There's overheads of going from Python to Java as well, which, that adds its own overheads. But
there's a question, and I know we're about to hit time. So there's a question also about cluster support and Modin versus Dask. And I thought maybe this case study would be helpful for
sure, let's do this.
Peter, who asked that question. So as Ponder, we're working and partnering with industry organizations to help them integrate and deploy Modin and identify opportunities for us to kind of build around the Modin ecosystem as Ponder. This is an example of where we're working with an AI platform company whose legacy infrastructure was built in Dask and highly optimized and tuned by their core engineering team. But even with such a talented team, they continued to run out of memory. It was difficult for them to maintain their Dask clusters. And so they were starting to think about alternatives to really speed up and optimize a lot of the pre-processing that their low code, no code solution supported. So we partnered with them, worked closely with the team. In a couple of weeks, we were able to demonstrate that Modin can act as a drop-in replacement for a bunch of their feature engineering work. We showed 2x speedups on a number of different workloads relative to the tuned Dask clusters that their engineers had set up. We also demonstrated improved memory management on certain workloads relative to Dask. And for them, the biggest thing was around maintainability and ease of use. So they were ecstatic when we told them that they no longer had to deal with partitioning and scheduling and manually optimizing and tuning that because Modin handles that under the hood for you. So hopefully that adds a little color to the Modin and Dask question that was raised. Other questions? And Antje and Chris, you'll have to tell me when we're at time.
Yeah, we're about at time. So why don't you finish your presentation, what you wanted to share, and then I'll summarize the questions.
Yeah, I mean, I think this is it. Really excited to tell you all about what we've been doing with Modin and at Ponder. If we didn't get to your question, feel free to reach out to us. Our emails are here on the page. And yeah, please pip install Modin and let us know what you think.
All right, thanks so much, Devin and Alejandro. I think we got through most of the questions. I think there were maybe a few very specific ones. One that we didn't get to a couple of years ago, we switched to NVMe drivers to load typical data files into memory faster. Multi-core benefits and disk speed benefits, etc. So if you have any additional links you want to share, maybe from Ponder or Modin documentation, any papers, feel free. And again, I think it's an interesting topic. We got a lot of discussion going on here, so thanks so much. And as you said, people are invited to reach out, right, for additional chats.
Yes. Devin at ponder.io or Alejandro at ponder.io.
All right, you got it. Thanks so much both for joining us today. I think we have to repeat maybe this session. It's a lot of interest here, and we will collaborate on maybe a few more assets together. Thanks so much. All right, and with that, I'm welcoming Justin to our virtual stage here. To talk a little bit from his work in the Amazon Alexa AI team, and specifically around DeepSpeed ZeRO. I think today we're learning using Nvidia GPUs and Kubernetes, and how to optimize large-scale distributed training jobs. Justin, the stage is yours.
Thanks. Hi, everyone. So my name is Justin. I'm an SDE on the Alexa AI team, or one of them at least. And I'm going to talk about some work we did as part of an effort to train very, very large language models. So let me just give a tiny bit of background as to why we wanted to do that in the first place. This graph over here, I hope everyone can see it. This kind of shows, oops, it's not what I wanted. This kind of shows the progression of kind of sizes of state-of-the-art language models over time. You can see back in 2018, it's somewhere around 94 million, which is very, very small by today's standards. Today, it's all the way up to 530 billion for the current state-of-the-art. So very, very large models. We don't necessarily have any direct use for these models. So the models that we run in production are very small. We have very tight latency SLAs. They typically run in something like 5 milliseconds. And then parameters somewhere under 100 million parameters. So quite a few orders of magnitude under these state-of-the-art models. But the reason why we want to train these models is because there's a concept called knowledge distillation. I'll share this link in the chat. I don't think we have enough time to get too into it, but the general idea is that you can have a very large language model that's very, very accurate, and you can use it as basically a teacher for a smaller model. So we'll have, a 50 billion, 100 billion parameter model that we just spend all these resource training, and then we use it to train our small models that actually do make it into production. So yeah, that's the basic idea, or the basic motivation for why we're doing this. Now, for training very large language models, just a couple kind of numbers we can get out of the way at first. The models are stored in half precision, which is kind of more standard practice today. So if you have half precision weights, let's say the primary model I was focusing on was our 50 billion parameter model. For a 50 billion parameter model, or just more generally, let's just say for X parameters. So if you had to store the half precision weights, oops. That's 2 bytes per parameter. That's 2x bytes, right? You have to store. So for a 10 billion parameter model, let's just go with the 10 billion, which was state of the art all the way back in 2020. That's a 20 gigabyte model. And if you're thinking, well, we have this, okay, this is a 20 gigabyte model, modern GPUs like A100s have 40 gigabytes of memory, this should fit fine, right? There's a few problems with this though. We don't just have to store the weights, we have to store the gradients as well, also in half precision. It's another 2x, so we're up to 4x right now. So that'd be 40 gigabytes for a 10 billion parameter model. And then we have optimizer states. And of these, these optimizer states are made up of, we have a copy of the gradients, or I'm sorry, a copy of the weights. Which is stored in full precision, so it's 4x. And then we have momentum, also full precision, so that's another 4x. And then we have variances. another 4x. Also, these optimizer states are for Atom, the Atom optimizer, which is all the rage nowadays. So if we kind of tally all this up, this is 16x. So our 10 billion parameter model, which is, you know, for a field like this, it's basically from the Stone Ages. This translates to 160 gigabytes in memory requirements. So now we have a real problem. We can't just put a copy of our model on a GPU and just train it, right? Like we would train any other model. There's quite a bit of engineering challenges that come from trying to run these models. The first thing that we just noticed is that we had to shard this model somehow. Now, typically in the field of training kind of larger models, there's a few different types of parallelism. There's data parallelism.
And Justin, just a quick question. Could you zoom in on the whiteboard part a little bit? Or maybe a little bit bigger?
Course.
Yeah, thank you.
Is that readable?
I think it's getting better.
Sorry about my
Yeah,
handwriting.
yeah, better.
Okay.
Thank you.
Great. Yeah, so we have data parallel, which is sort of like you have multiple replicas of your model, and then you just feed different data through them, right? And these can run in parallel. Problem with just using this is this block right here is a 160 gigabyte block, won't fit on a GPU, so we can't use it as it is right now. Second type of parallelism is model parallelism, where each slice of this model we'll just kind of slice it vertically. So for every given operator, we have different parts of the parameters on different GPUs, and then they perform each part of their computation. Okay. And this works, right? This solves our kind of memory problem a little bit, because instead of storing the entire model on a single GPU, we have kind of slices of each operator or each set of weights that are stored on each GPU. Some problems with this are that one, requires model refactoring, which is kind of a problem with a field like deep learning, where your scientists may be constantly wanting to try new sorts of models and new operators and things like that. Every time you want to try something new, it might not immediately work in a model parallel way. So you might have to have engineers or some expert come in and implement this for you in an efficient way. That increases iteration times and slows down progress. The other problem is that since you're dividing each operator this way, there's communication between the workers that's required within the operator. And for some operators that can become very large. So typically a single node in a deep learning cluster will have, like, let's say it's a P4D, an Amazon P4D, it'll have 8 GPUs on the single node. And those 8 GPUs are connected via very fast interconnect. It's called NVLink. Typically, the only way this is used is within the node, where the communication speed is quite fast. If you try to do this across nodes, it becomes very slow very quickly. Yeah, it's NVLink. If anybody wants to look that up. Okay, so that's model parallelism. And now we have pipeline parallelism. And that's sort of just partitioning the model horizontally instead. So if you think about the model as a sequence, right, we do the first part of the model and the second part of the model and the third part of the model. One thing you can do is you can say, okay, well, worker 1 gets the first part, and then worker 2, right, and so on. So worker 1 does this work and then it passes off to worker 2, and that handles the next part of the model, and so on. If you do things that way, you can split your model across your workers. The problem is that you get these things called pipeline bubbles, and this is and what you end up with if you do this naively is you have these huge chunks of time where you're just completely wasting your hardware. Now there's a lot of people have made some very clever optimizations to scheduling to kind of reduce the size of these bubbles, but you know, in some ways it's kind of unavoidable. Now the kind of what's very common in deep learning training is they use a combination of all 3 of these. It's called which at that point is called 3D parallelism. So DeepSpeed or ZeRO takes a slightly different approach. So what DeepSpeed is, what ZeRO tries to do is it tries to make everything, it tries to train everything in a data parallel way. Now, earlier we mentioned the big problem with data parallelism is that the memory requirements, right? We can't store 160 gigabytes on each GPU. We just don't have GPUs that big. So what ZeRO says is the kind of fundamental thing, that the fundamental insight from ZeRO is that all of this data, we don't need it all the time. Typically we go through, we'll go through a neural network, right, in layers. It's computed in layers. And once you get to a certain layer, you need the weights then. But after you get past that, you don't need them anymore. So maybe you could just ditch them afterwards. So what ZeRO does is it will partition, there's various stages, and at each stage it will partition more and more of this kind of data, right? So ZeRO stage 1 will just partition the optimizer states. So, oops, so this all gets divided by n, where n is your number of workers. So that cuts your memory requirements some. And then stage 2 will partition your gradients. And stage 3, which is what we were focusing on optimizing, will also partition the weights. So this 16x becomes 16 over n times x. Yeah. Now the thing with the thing with ZeRO is that, so since you kind of, the way they partition the weights is that once they're done using a weight, or well, the way they partition any tensor is that once the tensor is done being used, you look at the tensor. You look at the tensor like, you know, just some slice of memory. You'll just divide it into n segments, and then the first worker will get this segment, second worker gets this segment, third worker gets this segment, fourth worker, and so on. And when it's actually needed, what you'll do is you'll do an all gather operation so that each worker ends up with a full set of data. Once the operation's done, it will just drop everything that's not its section. So this gets us around a memory constraint. However, it introduces a lot of communication overhead. And once we actually started using this thing, what we found was that if you kind of graph performance, we measure this in T-flops per GPU. And then over here, you have GPUs. Ideally, what you'd like to see is you would like to see that as you add more and more GPUs, your performance, oh, sorry, this isn't T-flops per GPU, this is just T-flops. Your performance increases at a linear rate. What we actually saw was something like this, where performance started leveling off. It essentially wasn't scaling linearly. And the main reason for this is because of the communication expenses. If you look at a profile, we used NVIDIA's visual profiler. What you'll see is that, let's see if I can get this larger. What you'll see here is that you have these all gather operations that are required to gather their parameters, and only then can they be used. So let's say you're using some tensor, right? And what you'll see is the all gather for the tensor. And only then can you actually use it in the computation, right, on the GPU. And if you look at this, there's no what we call overlapping of communication and computation. As you scale the size of the cluster, this just increases in size. this increases in size. This stays fairly constant because this is just computation that's replicated across your GPUs. So how we kind of get around this is we say, well, this all gather, we don't have to, we can kick off this all gather a little bit earlier, maybe, right? We can say, like while we're using this tensor, in parallel, we can start kind of gathering the next one we need. And this is sort of, we didn't see a lot of this in kind of, when we took a look and started profiling DeepSpeed, we saw that there wasn't a whole lot of this going on. There was a lot of kind of very coarse synchronization primitives that were being used that were essentially saying we had to block on a lot more work than we have to in order to queue more operations. And then the results of that were you would see these very, very large kind of bubbles where you're basically not doing anything. You're just blocking on a bunch of stuff you don't need to. And so this kind of first optimization that we made was kind of one of the most impactful, took a lot of time as well, but it was sort of just going through it and kind of fixing the synchronization, making it much finer grained and only having a block on the things it needs to block. Took quite a while. It was a bit easier after some refactoring. But after this, we kind of, what we saw was kind of this more ideal case. So let me see if we can find bigger pictures. We saw this kind of more ideal scenario, right, where you have computation. So this stream 7 row right here represents computation operations, right? And they're basically going on continuously, and they're rarely blocked by communication, which communication is happening over here. You can see all these all gather operations in stream 26. So that kind of got us from something like 60 T-flops per GPU to, I think, it's written down here somewhere. Yeah, to 84. And then the next thing we took a look at was so in ZeRO, there's all sorts of decisions that need to be made about once we've gathered this tensor, should we let it go immediately? Is it reused anytime soon? If it's reused anytime soon, then maybe we can just keep it around, right, and avoid doing the whole gather, deallocate, gather kind of loop. Oh yeah, sorry about that. So T-flops is Terra floating point operation. Okay, cool. So yeah, you have all this logic basically that runs in Python that's trying to figure out how much longer until this parameter is going to be reused. Should I keep it? Should I let it go? All this is happening on CPU. And Python is kind of famously both slow and difficult to parallelize. And so what you'd see, let's see, what you would see is you would have these sort of large blocks of time where the CPU is just trying to make decisions about what to do with these tensors, and it is so slow that it basically is keeping it isn't queuing work fast enough for the GPU to consume. So since Python is difficult to parallelize, what we did was we just cached all these decisions. They're typically the same from run to run, and so if we only do this once, there's much less thinking the Python process has to do. It can just focus on feeding work to the GPU as fast as possible. And we get fewer bubbles in the computation stream. This netted us about 4 teraflops per GPU. Define a tensor. So a tensor is just a tensor is kind of a mathematical object, mathematical concept. It's just an n-dimensional array. So think about it as a collection of numbers with some shape, right? So you could have a tensor that's shaped 2 by 2. which has 4 numbers in it. In our case, they're either floating point 16s or floating point 32s. Okay. So anyways, we have we do this caching, much less kind of thinking the Python process has to do. So it just focuses on keeping the GPU fed with work, which means the GPU is working more of the time, rather than just sitting idle. Gets us about 4 teraflops per GPU, up to 88. The next thing we looked at was that, so you have all these all gather operations that we need to gather parameters, gather gradients. So a lot of the times what this ended up looking like was a bunch of very small all gather operations. And for various reasons, it's very difficult to parallelize communication collectives in Nickel, which is NCCL, which is the underlying communication library we were using. And so what we opted to do here was we opted to kind of batch these tiny little communication operations. The reason why it's a bit more efficient to batch is because if you're running a lot of small communication collectives in series, there's a couple problems. Number one is you don't completely use your bandwidth that you have. And the number two is that you're launching a lot of small kernels, and launching kernels has a fixed overhead. So by kind of batching a bunch into a single kernel launch, you amortize a lot of that fixed cost. And then, yeah, there's this kind of interleaving that we had to do with the tensors in order to make sure the correct data ends up at each worker. I don't think we need to go into that too much. This gets us from 88 teraflops per GPU up to 102. Now with memory, all gather, define all gather. So all gather is what it is if you have a bunch of workers in your cluster and they all have some piece of data, right, that's different. The result of the all gather operation is that each worker will have all pieces of data from all workers. So something like this, if you're interested in learning more about it, might explain it in a little bit more detail. But that's basically what all gather does. In our case, we have tensors that are sharded across workers. So each worker has its own little section of the shard. Has its own little section of the tensor. And after the all gather, all workers will have all sections of the tensor. Okay. One thing we found that was actually a big problem was memory consumption. Even after sharding, it's kind of more of a PyTorch quirk than anything else. Okay. It's kind of more of a PyTorch thing than anything else. But generally allocating memory, in general, allocating memory is expensive. It's very expensive on GPUs. What PyTorch does to get around this is they have what's called a caching allocator. So can this page be shared? Yeah, I can share it. Let me do that right now. What PyTorch has is a caching allocator. So let's say you need to allocate memory to create a new tensor. It will allocate the memory for you. But once you're done using the tensor, instead of deallocating that memory, it just keeps it. And it has all sorts of smart kind of ways to break up this memory and ensure that there's minimal fragmentation and things like that. But the end result of this is that when you ask for PyTorch for memory, when you create a new tensor, it doesn't necessarily allocate memory there. And when you destroy that tensor, it doesn't necessarily deallocate the underlying memory. There's a bit of a kind of implementation problem with this, though. If you create a bunch of tensors, the memory is preserved right then and there. And similarly, if an operator outputs a tensor, the memory is reserved right then and there. To kind of explain why this is a bit problematic, let me just kind of explain real quick about how computation on NVIDIA GPUs works. It's an asynchronous computation model. So let's say you have a PyTorch tensor that's on GPU and you do like tensor plus other tensor. When that bit of code finishes, that result isn't necessarily available yet. All that does is queue the work on the GPU. Now, if you go to print it or something like that, PyTorch is smart enough to know that it should synchronize, right, and wait for all work to complete before it prints out the results. But generally, that's kind of how it works, right? Things are just because you run something in Python, all you do is queue it and it runs on the GPU. So the reason, back to kind of why this memory thing is problematic. Where should there run? Infected URL. Oh, that's weird.
Yeah, Justin, I think it's an internal URL that external people cannot access, right? So
I got it. Okay.
Yeah.
I could try to put it in something more publicly accessible later.
Yeah, thanks.
Yeah, not trying to give anyone any viruses or anything, I promise. So you have all this computation happening asynchronously. And what the Python process is doing is it's just queuing up as much work as possible. And ideally, the Python process gets way ahead of the GPU, and the GPU has a huge queue, so the GPU is just constantly having something to do. But if you have this kind of memory model where as soon as you perform an operation, as soon as you queue an operation, you reserve the memory. Then what happens is you build up a large queue, and the kind of intermediate results for all those operations of the queue, you've already reserved memory for them. And doing this can get you to run out of memory very, very quickly. What happens when PyTorch kind of runs out of memory in its caching allocator, the results for distributed training are pretty disastrous. First it has to flush the cache and then try to reallocate. But before it can flush the cache, it has to synchronize on all operations that are using memory that it holds, because it can't just get rid of memory that might still be in use. So that alone takes quite a long time. And then afterwards, to refill the cache, it requires that memory to be allocated again. And perhaps the worst part of this is that different workers aren't guaranteed to do this flush at the same time. It's one thing that takes a long time, but so if you think about like an all gather operation or an all reduce or any collective that involves all workers, it doesn't finish until all workers have finished. So if any one worker, it takes a long time because perhaps it's doing something like a flush, then that slows down the entire cluster. And we have, so our training cluster, the one we were using is 128 NVIDIA, AWS P4Ds. So 128 times 8, that's 1,024 workers. So as you kind of increase the size of your cluster, the probability of any one worker doing this during your collective gets quite high. So this was a huge problem that kind of we uncovered after fixing all these synchronization issues. And to get around this, so we're sort of running out of time. I'll sort of just fly through the rest of this. To get around this, we kind of we made some optimizations in PyTorch's collective operations. They're all gather and reduce scatter, and essentially what they do is they try to avoid redundant memory allocations. This part of the rearranging operation, you need a buffer as an intermediate kind of workspace to do the rearranging. We found ways around that using different combination of different APIs and different interleaving mechanisms. Yeah, and then there's a bit about optimizing the grad norm computation in the optimizer step. But anyways, the kind of end result of this is we got it up to about 116 teraflops per GPU. This means that our 50 billion parameter model trained in about 17 weeks versus 35, 36, which is, saves a lot of time, a few $1 million. Yeah, we can kind of start on questions now. I'll try to go through them.
All right. Yeah, thanks so much, Justin. Really impressive the work you've done in the team there. So yeah, let me see a couple of the questions. We had questions a little bit earlier when you started discussing data parallel versus model parallel. Not sure if you touched on that later, but can you describe how parameter tuning happens on data parallelism?
Sure. So parameter tuning, do you mean like hyperparameter tuning?
I think that's what the question intended to ask, yeah.
Sure. Yeah, so hyperparameter tuning can be done in the same way as if you were just running a plain kind of single host, single worker training job. So typically how this would work is you would run your training script runs on all work. There's a copy of your training script that's run for each worker. And so you can just change the parameters in your training script and all workers would end up with the same hyperparameters. The fact that this is run in a data parallel way can be mostly abstracted away from the modeler.
All right, and we had a question, does ZeRO discard the weights of neural network? If so, how does it handle feedback networks like RNN?
Mm-hmm. So yeah, no, ZeRO will discard, it doesn't ever, so if you look at the entire system, you will always have the data, right, for a given tensor. What it does is it will remove redundancy. So if you have a copy of a tensor that's the same on every single worker in your cluster, that's redundancy. To get around that, you basically what they do is they say, okay, well, worker 1 only needs to keep the first section of this tensor, worker 2 just keeps the second section, and so on. As for how RNNs are run, what you could do, what it would be modeled as is kind of just separate forward passes in a for loop, right? And you just treat like a single step of the RNN as the model, and the whole thing would be run in a loop.
All right, perfect. And another question, seems like the solution uses a lot of clever tricks to optimize relatively low-level CUDA, GPU memory, core usages. Can these ideas be implemented with a higher level of abstraction?
With a higher level abstraction. Could you clarify the question a little bit? Whoever asked, is that kind of getting at what tricks can I as a model trainer use to make my runs go faster, or is it something else? Let me see if they. Yeah. Okay.
Yes. Yeah.
Cool. So yeah, like these optimizations, you're right. These are optimizations within DeepSpeed. So if you use DeepSpeed, then hopefully you get these for free. You don't have to do much. While we were doing the benchmarking, though, we did find some kind of we found some inefficiencies in our training code, and the kind of big ones were the way we were doing gradient checkpointing. So gradient checkpointing, for people who don't know, is so typically when you train a model, right, you keep the activations from each layer all the way through the forward pass, and then you only deallocate them after you do the backward pass. Gradient checkpointing says you can keep every nth activation, and then you just recompute the activations while you're in the backward loop, right, while you're in the backward pass. So we found that we started out with kind of checkpointing every square root of nth layer, but this actually consumed a lot more memory and led to the problems that I mentioned earlier, with kind of memory consumption dramatically, hurting our scalability. So we found that checkpointing every nth layer, or every we found that just doing a checkpoint every layer was quite a bit more efficient for memory wise, and didn't increase our compute enough to kind of hurt scalability or performance. The other big one was that we found that for our embedding layers, we had vocabulary sizes that weren't a multiple of 32, and this is pretty inefficient, because in CUDA kernels, the computation is scheduled in warps, which is 32 threads. So we found that having the vocab a size of 32, multiple of 32, made things a lot more efficient. The other thing was we found some issues in our model. Between the checkpointed steps, we were returning both layer normed and unlayer normed activations, which essentially doubled the memory consumed by activations and resulted in a lot of, again, memory issues that in turn led to performance going down.
All right, thanks, Justin. And another question, just for clarification, did you say you need to optimize and customize the PyTorch DDP library?
We didn't. So PyTorch has a fully shared data parallel module now, as far as I know. So what we optimized was DeepSpeed, which is Microsoft's library. So DeepSpeed was the original implementation of DeepSpeed ZeRO. And the sort of stage 3 sharding is also now implemented in PyTorch, but that's not what we optimized. We optimized DeepSpeed.
And we do have another question here, a little bit longer one, if you want to read that. But basically, do you have recommendations for achieving DeepSpeed ZeRO results for vision-related tasks?
Yeah, so let me just try to read the context real quick. My primary development and my model training code for Ensemble CV had those tracing on stage 1, geometric map on stage 2, and rendered artificial on stage 3, super slow, point space analysis and STM. Okay, so this application is training. So those stages are you using DeepSpeed ZeRO stages? And it's quite slow. And also, so for training performance, no, just naive coding on TensorFlow. I see. Okay, so for training, at least, I would say most applications do not need the full kind of stage 3 sharding. It's just not necessary for most of the models that people work with. These really large language models are typically only kind of trained by very large resource labs with tons of resources. So for kind of like self projects, you're probably not going to be spinning up a cluster like this, which costs like $4,000 an hour to train these very large models. So you can usually get away with simpler approaches to training for more typical models. If your training is going really slow, I would suggest first profiling it. Nvidia has a really great visual profiler. The screenshots I've been sharing are that's where they're from. And from that, you can find out a lot of things. You can find out, usually that's good enough for you to find out kind of where your performance losses are coming from. The most typical thing that I've seen, at least, is that synchronization not being done correctly, which ends up with you just having these huge chunks of time where you're not using your hardware at all. And then if you need to, you can really dive into the actual CUDA kernel implementation and optimize that. But for most people, the implementations are already optimized enough, and there's not too much more they would need to do.
All right, I think that's the questions I can see here. Maybe a last one from me. Working with DeepSpeed, how would you, Justin, from your experience, like compare the project to distributed frameworks like Ray that gained a lot of popularity recently too, right?
Yeah, so DeepSpeed is DeepSpeed is a lot more kind of specific in its mission than something like Ray. DeepSpeed specifically for training very, very large language models. I don't have too much context on what Ray does. Let me just see if I can find out in like a minute.
Yeah, basically Ray helps you to distribute and scale Python in a very efficient way. So they have libraries for model training, tuning too. So I was just wondering whether you looked at that as part of this work with DeepSpeed.
Yeah, so it looks like, let's see. So it does distribute deep learning though, so supercharge, let's see. Trying to get through all the marketing speak and figure out what it actually does. It kind of looks like what this does is just sort of plain data parallelism across your cluster. And I would say this is kind of Ray's, what it looks like to me is it's sort of just but a lot more user friendly, right? If you're not, what you're doing isn't too crazy. If you just want to train a model and scale it across your cluster, and you don't want all this control over, you don't need to shard it. You don't want all this control over various parts of the training process that affect performance. It seems like a good option. DeepSpeed is specifically for sharding things that are, where your model doesn't fit on a worker without a lot of kind of engineering workarounds. Let's see. Go through the questions. What percentage
don't worry.
do you reduce the training?
We can connect afterwards on that as well. Yeah, we have 2 more questions. If you have time, maybe quickly, how much % did you reduce the training time?
We roughly have the training time. We roughly have the training time. It was going to be about 35 weeks before, and then after the optimizations, it was about 17 weeks on 128 P4Ds. And will you contribute? Yes, it's already been contributed actually. So it's we did open source the optimizations. And this only works on Kubernetes infra. No, it works on it's infrastructure agnostic. We just happen to run our cluster on Kubernetes, but you could run it any way you wanted.
All right, I think that's a wrap. And thanks so much, Justin, for sharing all of the work you've done here with DeepSpeed, sorry. And we have recorded the session, so it will be posted here on our YouTube channel. I've just posted here real quick. And also somebody asked for the upcoming sessions. Have a look at our meetup. We have announced already the next month session. In July, we will talk more about NVIDIA TensorRT and NVIDIA Triton, and have a community member, Francesco Puccetti, talking and presenting to us. He built a great demo how to blur faces. So he's going to show us a segmentation model using those technologies. And we also have a session and talk about PyTorch's new native integration with Amazon S3 object storage for ultra-fast data loading. So there's a new integration, and we're going to see how that data pipe works. All right. And with that, again, thanks so much, Justin, and have a good day, everyone. Thanks for joining us today.